So this is a mixing problem. We're going to be mixing 10 kilograms per second of air at 400 degrees Kelvin with 12 kilograms per second of combustion products at 600 degrees Kelvin in a steady flow adiabatic mixture. We need to determine the Cp and gamma and temperature of the mixture and assume calorically perfect gases with properties in the below table and neglecting kinetic energy changes. So if we sketch a mixer here with two inlets with air going into the mixer at 10 kilograms per second and a temperature of 400 degrees Kelvin, and the combustion products, M dot C, going in at 12 kilograms per second at a temperature of 600 degrees Kelvin. And due to the conservation of mass principle, we know that the sum of the mass flow in is equal to the sum of the mass flow out, so that is 22 kilograms per second. And from the table, in table 2.2, we can get the Cp, R, and gamma values of air. So the governing principles for this problem are the conservation of mass, momentum, and energy. Because we're finding temperatures and neglecting kinetic energy, we need to incorporate those principles because they govern the world and this problem. And also the kinetic theory of gases, because air is ideal. And the governing equations, we've got Navier-Stokes equations and also these ratios of the contributions of both the air and the combustion products, contributions towards the temperature, the Cp and gamma values of the mixture. And of course, conservation of energy, the second law of thermodynamics, which is TdS delta Q, and the conservation of mass, which is that the mass flow rate of the mixture equals the mass flow rate of the combustion products plus the mass flow rate of the air, which is why we see that the M dot of the mixture is 22 kilograms per second. And the assumptions that we need to make for this problem: steady flow. It's not one-dimensional because we're mixing fluids. Adiabatic, neglect kinetic energy changes, and calorically perfect. Those three were given in the problem statement. Complete stoichiometric combustion. And the fuel is C10H22 with oxygen, and they mix to make combustion products, and the outputs of the C10H22 fuel and oxygen will be H2O and CO2. Those are common outputs, and I will explain later in more depth. So first we need to mix the fuel with oxygen, because we have oxidizer and that creates combustion products, and then we mix the combustion products with air, and that gives us the mixture that we're trying to find properties for. So we're going to do two mixing problems, two ratios of components. Now we need to ensure that the mixture is in equilibrium. We need to set the left-hand side, which is the components of the mixture, to the right-hand side, which is the outputs. And we made the assumption that the outputs would be H2O and CO2. Those are the components of the mixture, which is the mixture called the combustion products. So we need to set up an equation for carbon to balance it and assume that x equals 1 to solve this equation. So then we plug in 1 for x, and we have 10 carbons associated with x. And on the right-hand side, on the right of the equation on the bottom, we have only one carbon associated with the W, and that gives us W equals 10. Now we need to set up an equation for hydrogen. On the left side, we still have x equals 1 associated with 22 hydrogens. And on the right side, we have 2 hydrogens associated with Z. So Z equals 11. Now we can set up an equilibrium equation for oxygen. We have Y associated with 2 oxygens on the left, Z associated with only 1 oxygen, plus W associated with 2 oxygens. And we know Z and we know W, so we can solve for Y. And Y is going to be 15.5. So now we have 10 parts CO2 and 11 parts H2O for the combustion product mixture. And we can take from table A2 the CP gamma values for those components. Now we have enough information to actually find CP of the combustion products. So this equation has been written out for the mixture of air and the combustion products, but first we need to find the actual CP of the combustion products first. So that's from mixing CO2 and H2O. So this equation is the same regardless of if you use m dot or m, so I'm just going to erase these rates because we don't know the rates of CO2 and H2O. We only can find from a table what the molar masses are. So plugging in the CP values for each, and I'm just going to rearrange that to match the format of the bottom equation. But we have 11 parts H2O multiplied by the mass of H2O times the CP associated with H2O. And then we could do the same thing for CO2 and make sure that all the masses are multiplied by their associated ratio of the mixture. And then on the right, 49 is the molar mass of H2O. And yeah, just plugging everything in, we can get the CP of the combustion products. And then we can also find the gamma of the combustion products as well. And that's this equation right here, just replacing the gamma for all the CPs, and we can find the gamma of the combustion products is 1.301. So now we've done the first mixture portion of this problem right here. Now we need to do the second one, which is air and the combustion products. So we know the mass flow rate of air and the combustion products. So we can use that information in our ratio. And we know that they're not split up into parts, so we don't need to multiply them by, like, for example, 11 or 10, which we did before. So as you can see, the gamma of the combustion products was used to find the gamma of the mixture. And so deriving the ratio for the temperatures of the air and the combustion products mixture, we get an equation, and I'm going to replace it with the one above because the one above was incorrect. And we can plug in everything we know about the mass flow rate of the air and the combustion products and the CPs and the temperatures and find the temperature of the mixture. And so that is our second mixture problem. And we know that our answers look alright because the values for each mixture that we did were in between the values of the components. So really at the end of the day, you want to be making sure that you're balancing each of the components, each of the elements on the left-hand side, which are your ingredients for the mixture, with the right-hand side, which are the components of the mixture. Thanks for watching, and if you have any questions, just leave them in the comments.